Yeah, it is recording. It has like a little recording button at the top.
Can you hear me, Ashley?
Yeah. Can you hear me?
Yes, is it recording?
Yeah, it is recording.
Okay, perfect. Sorry about that. Glad I caught it though. Anyhow, so just to reiterate, lectures are Monday, Wednesday, Friday, 11 to noon. Study groups are Tuesday, Thursday, which start tomorrow. And we are going to be having our first exam released on Gradescope, which is going to be, it's going to be released on Friday. You guys will have, I think, 24 hours to take it and upload it back to Gradescope. If you have any questions about using Gradescope or about the exam, a great people to ask would be your study group leaders, because they can kind of help you figure out all the intricacies in using Gradescope and Canvas if you haven't already used them for another course. So today we're going to be talking about some organic chemistry related Gen Chem concepts, just to review. I'm still waiting for screen sharing to start working again. Perfect. We're going to be talking about hybridization, formal charge, and resonance, and we're going to learn how we draw structures in organic chemistry. You probably will have seen most of the molecules that we're going to talk about before, but at the end of lecture, we're going to show you how we draw them differently. So the first concept that we're going to talk about today is hybridization. So you probably remember this from Gen Chem, but molecules are either that have a steric number of 2 or a steric number of 6. That is, the central atom has either 2 or 6 groups around it. They have sp hybridization. And in general chemistry, 2070, I know we referred to this hybridization as sp plus p plus p. However, in organic chemistry, we typically just refer to it as sp hybridization. So I made sure to put the plus p in parentheses, because this was something that was really confusing to me when I first started orgo. So it's still there, but we just refer to this hybridization scheme as sp. In sp hybridization, we have 2 sp hybrids and 2 p orbitals. That's where the plus p would come in. The molecular geometry for this hybridization scheme is typically linear if you have 2 bonds. Remember that when I say 2 to 6 groups, that could be a bond connected to an atom, or it could be a lone pair. So the geometry can vary with bond number. Also, the angle between the bonds is 180 degrees for sp hybridization. However, it's important to note that lone pairs, if you remember, take up more space than bonds. So the bond angle will decrease if I have a bond and a lone pair around my central atom versus if I have 2 bonds. So I'm going to go ahead and draw out the sort of ingredients for our sp hybridized central atom. We've got our 2 sp hybrids right here, and we've got 2 p orbitals. And those are going to combine together where we have our 2 hybrids, kind of like this, and we have 2 p orbitals. One of them is sort of going up and down, and one of them is coming straight in and out of the plane of the board. So this is what our hybrid orbital for an sp hybridized molecule would look like. All right, so the next hybridization scheme we're going to talk about is sp2 hybridization, known in Gen Chem as sp2 plus p. Molecules that have a steric number of 3 or a steric number of 5 are going to have this hybridization. So that means that basically your central atom, if it has either 3 groups or 5 groups, so 3 lone pairs or 3 lone pairs or bonds, or 5 lone pairs or bonds around it, they're going to have this hybridization scheme. It includes 3 sp2 hybrids and 1 p orbital. And the molecular geometry for the sp2 hybridized central atom, the molecular geometry for an sp2 molecule is going to be generally trigonal planar if it has 3 bonds. as I'm sure you remember from the second prelim material for 2070, if you have 2 bonds in a lone pair, you could have a different type of shape. Also, the bond angle for sp2 hybridized molecules is 120 degrees, but that can decrease with the number of lone pairs. So again, I have them already drawn out this time. The ingredients for our sp2 hybridized orbital include 3 sp2 hybridized orbitals. You can see those there. And we only have 1 p orbital here. So those are going to combine to create this molecule here. We have our 3 sp2 hybrid orbitals arranged like this. And we have this p orbital coming in and out of the plane of the board. You can see this is like the front lobe. So this part would correspond to this front circle right here. And then we have this back lobe, which is represented by this circle at the back. So our last hybridization scheme that we need to talk about is sp3 hybridization. The molecules are going to have a steric number of 4, so the central atom has 4 groups around it. It includes 4 sp3 hybrid orbitals, and they are arranged in a tetrahedral shape. I'll draw your attention to down here. The kind of recipe, if you will, for making an sp3 hybridized molecule is just 4 sp3 hybrids, and they're arranged in a shape like this. Again, the geometry is tetrahedral if you have 4 bonds, and the bond angle is 109.5 degrees between each of the bonds, if you have 4 bonds, again. So we are going to go ahead and do a little review to practice what we've just talked about. I would love it if you guys would be willing to participate as we talk about the hybridization schemes for the following molecules. So we start off with this water molecule. Can anyone tell me what the hybridization scheme for this first molecule here is? We've got 1, 2, 3, 4 groups. So you're welcome to just shout it out, or you can comment in the chat. Oh, I see we have a question. What was the bond angle for sp3? The bond angle was 109.5 if you have 4 bonds. Yep, I see if you aren't looking at the chat, somebody just posted that the water molecule was sp3 hybridization, and that's definitely correct. This is something that might trip people up. There are 4 groups around this molecule, so it's sp3. Remember, bonds can count as groups. All right, moving on to this amide group down here with the nitrogen. What about this group? Well, I'm sorry, what about this molecule? What's the hybridization scheme?
sp3.
Yep, this is sp3 as well. We have 4 groups around it, 3 bonds and a lone pair. So that's definitely sp3. Now, we're going to go down to our xenon difluoride. Don't get confused. This molecule does show the lone pairs using our wedge dash format, but these are lone pairs. Does anyone want to talk about the hybridization scheme for this molecule down here? Or post it. That's fine too.
Is it sp2?
Yep, this molecule is sp2. Very good job. We have 5 groups around our central atom. We've got 1, 2, 3, 4, 5. So this is going to be sp2 hybridized. Now, back up to this molecule with the 3 consecutive carbons, all with double bonds. You might recognize this problem from one of Dr. Lee's practice exams for 2070. I know I definitely do. Does anyone want to talk about the hybridization scheme for this molecule?
Would it be
Go ahead, Deborah.
Would it be SP? I don't know.
Yes, it would. So this problem, we have our central atom as a carbon, and there are two different groups around our carbon. This one is interesting because, I mean, most of the problems where we talk about hybridization, it's normally single bonds, or a lot of time it's single bonds. But here there's two double bonds around our central carbon. That's two groups. This is most definitely sp2 hybridized. Good job. I'm sorry, this is sp hybridized, not sp2. Now, down to our SF6, which is another molecule that Dr. Lee references a lot in practice problems. Can anyone give the hybridization scheme for SF6, please?
SP.
Yep, that's very good. This molecule is sp hybridized, and it has 6 different groups around it. And lastly, we have our HCN down here. Can anyone give me the last hybridization scheme for this molecule?
SP.
Yep, good, Alex. So this is sp hybridized. There are 2 different groups around our carbon. So I'm going to go ahead and write that. Wonderful. You guys are pros at this. Okay, we have a question for why SF6 is SP. There are 6 groups around our SF6, and if we have either 2 groups or 6 groups, a molecule is going to be SP hybridized. Does that make sense, Julia? Perfect. Okay, so we're going to talk briefly about our next topic, which is formal charge, which is very important. Again, this is review, so just bear with me as we talk about these concepts, which I'm sure you learned in 2070, but which are super important for doing the Gen Chem stuff that we're excited to delve into. So if you remember, some easy steps for calculating formal charge, you look at how many electrons the central atom should have around it, or how many electrons it wants to have. And you also look at how many electrons it does have. And then to calculate the formal charge, you take the number of electrons the atom should have, and you subtract the number it does have from that number. And then I just wrote up some brief reminders to keep in mind. Each bond has 2 electrons, and 1 goes to each atom. So let's look at this example down here. We have an oxygen right here, and let's say we want to figure out the formal charge just for that atom. Well, we have 3 bonds around our oxygen. So in each of these bonds, 1 electron is going to go to the oxygen, and 1 electron is going to go to the other attached atom. So if we want to find out the formal charge for the oxygen, I'm going to go ahead and count up how many atoms the oxygen does have around it, which is 1, 2, and then 3, 4, 5. So this oxygen has 5 electrons around it. And then if you remember, oxygen always wants to have or should have 6 electrons around it. So it wants to have 6. So if I subtract 5 from 6, I get +1. So the charge on our oxygen is equal to +1, which I'm just going to show by using a positive charge. And remember, to get the overall charge on a molecule, I would add up all the formal charges for all the atoms. Since oxygen is the only atom in this molecule which doesn't have the amount of electrons it wants to have around it. We see the carbon has all the electrons it wants. The hydrogen, of course, is good with just a single bond. This molecule is going to have a formal charge of just +1. So the formal charge of the overall molecule is equal to the formal charge on the oxygen. So
Can you repeat that? Sorry.
yes, the formal charge on the overall molecule in this case is equal to the formal charge on the oxygen, because to get the overall formal charge, we would add up the charge on all the atoms, and we only have one atom in this molecule that has any sort of formal charge at all. Now that's going to be different for each of the examples, but let's go ahead and take a look and see how that might apply. So for this molecule right over here at the end, let's take a look. We're going to first do this carbon. Carbon wants to have, or should have, 4 electrons around it, right? So I'm going to go ahead and count to see how many it does have. Wants to have 4. So here, I'm going to divide each of these bonds in half because, again, 1 electron goes in each of these bonds to our carbon, and 1 electron is going to go to the other molecule. And it got cut off, but there is a CH3 that's at the other end of this, if that wasn't clear to any of you. So again, this carbon wants to have 4 electrons around it, and if we count, it does have 4 electrons around it. So is there a formal charge on the carbon? Can you guys see now? Perfect. There isn't a formal charge on any of these carbons right here, or I'm sorry, on this particular carbon. So we're going to go ahead to the next molecule and see if anything's different. Or I'm sorry, to the next atom and see if anything's different. For our nitrogen, we know that nitrogen wants or should have 5 electrons around it, right? So let's go ahead and see how many electrons it does have. It has 4 bonds, so I'm going to count the electrons that go to the nitrogen. 1, 2, 3, 4. There are 4 electrons around our nitrogen. So nitrogen has 4. Again, just as in our oxygen example over here, I'm going to subtract the 2 numbers since they're different. The amount it should have, the amount it should have, and then we subtract the amount it has, and that equals +1. So nitrogen is +1. And because nitrogen is the only atom in this molecule that has any sort of charge, our molecule has an overall charge of +1, just like the last example that we did over here. Does that make sense? Let's go do another example.
How do you figure out the central atom? Like, it was a C or N, which was the central atom in this case?
That's a good example. In this case, for formal charge, we don't exactly need to look at what the central atom is per se. We're just going around to kind of all the atoms and making sure that they all have the amount of electrons around them that they should have. Krinal, do you have a question?
Yeah, so for the oxygen example, there is 1 less electron than there should be, right?
Yes, exactly.
But for the nitrogen, it's sharing 4 electrons, but it needs 3. So why isn't it -1?
That's a good question. How many did you say it needs to have again?
3?
Well, it wants or needs to have 5. Where you're getting the 3 from is that in order to keep a neutral formal charge, I'm going to draw it up here where there's space, nitrogen needs to have 3 bonds. So I'll go ahead and draw that since you brought it up. In this example, nitrogen has its 3 bonds, right? 1, 2, 3. But if we count up the number of electrons that are around the nitrogen, we see that it has 1, 2, 3, 4, 5. And if you were to look at a periodic table, I believe you would see that nitrogen is in the 5th column. So that's also where we're getting the 5 from. Does this kind of answer your question?
Yes, thank you.
Yeah, no problem. Okay, let's go do another example, which actually, again, involves nitrogen. We see here for this nitrogen, again, it wants to have 5 electrons around it. Let's count up how many it does have. Each bond counts for 1 electron towards our count. So 1, 2, 3, 4, 5, 6. This nitrogen has 6 electrons around it. So again, I'm going to go ahead and subtract the amount of electrons the nitrogen does have from the amount it wants to have. 5 minus 6 equals -1. So this nitrogen has a minus charge on it because it has 1 more electron than it wants to have. And it's important to note that in, I think, all of these cases, the octet rule, where you want to have 8 total electrons, shared or not, is being maintained. I'm just going to bring that up. Like we have our 2, 4, 6, 8 electrons around this nitrogen, but we also have 2, 4, 6, 8 electrons around this nitrogen. The difference is that for formal charge, a bond only counts for 1 electron instead of 2. So don't get those two mixed up. And back to our example, because the nitrogen was the only charged atom, this molecule has a negative charge. Now I'm going to go ahead to our next example, which is right over here. Our oxygen wants to have 6 electrons again. And let's count up the amount of electrons it does have. 1, 2, 3, 4, 5, 6. Because each bond counts for 1 electron. So this oxygen, does it have a formal charge on it? This oxygen does not have a formal charge. Because 6, that's the number it wants to have or should have, minus 6, which is the amount it does have, equals 0. Now let's look at another oxygen, which is down here in the same molecule. Again, it wants to have 6, but let's see how many it does have. 1, 2, 3, 4, 5, 6, 7. So this oxygen has 1 more electron than it wants to have. So it's going to have a negative charge. And now let's look at a sulfur molecule. Sulfur, if you look on the periodic table, is in the same column as oxygen. So it wants to have 6 electrons. If we count how many it does have, 1, 2, 3, 4, 5, 6. So the sulfur, just like this oxygen up here, has the same amount of electrons as it wants to have. So its formal charge is 0. And because all of our atoms, we've looked at their formal charge. If you're wondering why I keep ignoring that random carbon, it's because most of the carbons, well, basically all of the ones in this example, they already have 4 bonds around them, so they're good. Atom has a formal charge of -1. Now moving on to our very last formal charge example. We're going to go ahead and count. We're only going to do 1 oxygen because in this molecule, the 2 oxygens, they basically have the same configuration. They both have 3 lone pairs and 1 bond. So oxygen wants to have 6 electrons. Let's count how many it does have. 1, 2, 3, 4, 5, 6, 7. So both of these oxygens have 7 electrons around them. If I subtract 7 from 6, I get -1. So both of these electrons, both of these oxygens have a minus charge. Then moving on to sulfur. Sulfur also wants or should have 6 electrons around it. If I count how many electrons it does have around it, 1, 2, 3, 4, 5, It only has 5 around it. 6 minus 5 equals 1, positive 1. So sulfur has a positive charge. Now this is the only example on this page where the formal charge, we're going to have to do the math here to add up all of these individual charges to get the overall charge on our molecule. And would anyone like to tell me what plus 1, minus 1, minus 1 all add up to be equal to?
Is it minus?
Yep, very good. So this molecule, I'm trying to figure out how I can draw this in a way that makes it obvious. The overall charge of the molecule is going to be minus 1, like that. Does everyone understand how I got to the minus 1 for the overall charge of the molecule? Okay, somebody's asking why we can disregard the CH3. Well, let me draw another example up here. And if you didn't know, when you see this R, that just stands for rest of the molecule. So we can kind of ignore that. And I'm gonna move this over here so it's clearer. There we go. So in this molecule, let's find the formal charge of our carbon. So carbon wants to have 4 electrons around it, or should have 4 electrons around it. And if we count the amount of electrons that it does have around it, 1, 2, 3, 4, then we can see that it has the 4 electrons. And again, what's the formal charge on this molecule, on this carbon right here? If the carbon wants to have 4 and it has 4. Well, just as in a couple of our other examples, the formal charge on the carbon is equal to 0, because 4 minus 4 equals 0. So whenever you see a CH3 attached to a molecule, you automatically know that this is a neutral atom. It doesn't have a formal charge because it wants to have 4 electrons around it, and if it has 4 bonds around it, which it pretty much always does, then it's not going to have a formal charge. Does that answer your question, Taylor?
Yes. So if it was something else, though, it might have the charge that you would add.
Exactly. Like if I drew a nitrogen with 4, I'll go to my example down here. This is the same one from right here. Only here it's a triple bond, but it's still the exact same idea. This one has a formal charge because nitrogen doesn't want to have 4 bonds. Nitrogen wants to have 5 electrons around it, so it needs 3 bonds to both maintain the octet rule and to make sure that it has the amount of electrons around it that it wants. Does that make sense?
Yes, thank you.
Okay.
I have a quick question. You wrote that each bond has 2 electrons, and then you put an arrow, 1 goes to the atom. What does that mean?
So that's just like what I was saying before, how in any sort of bond, like this bond, for example, 1 electron from this bond is going to go to the nitrogen, and 1 electron from this bond is going to go to the hydrogen. Now, this bond can contribute to both of the atoms meeting their octet rule. Like both of these molecules follow the octet rule. They all have 8 electrons around them. Count shared electrons. Like you can count the 2 electrons in this bond are going to both go to the carbon. And it's going to be able to have, say it has 8 electrons total. But when we're counting formal charge, we need to know how many electrons are directly on that atom, if you know what I mean. So
Yeah.
you can just split this bond in half, and 1 electron is going to go to our hydrogen in this bond, and 1 electron is going to go to our nitrogen. And that's how I keep getting the number of, oh, this has 4 electrons around it. Does that make sense?
Yes.
Wonderful, wonderful. So we're going to talk about a concept which will become the bane of your existence for the next at least year, which is resonance. As you probably remember a little bit from 2070, resonance shows the localization of electrons on different atoms in a molecule. So the way Dr. Rutledge liked to explain Rutledge to us last summer was a game of hot potato, where you have a potato that's right out of the oven and it's flaming hot, and if you hold it for too long, it'll burn your hand. So imagine that there are 50 people all in a circle. Like, we take all the OCSP students and we stick them in a circle, and you all are randomly trying to throw the potato to the next person because none of you want to get burned. Well, it's the same sort of idea. If we have a negative charge in a molecule, like we were talking about earlier, some of these atoms in this molecule, for example, have a negative charge, that's not super stable. And as we will also talk about a lot this summer, atoms really love stability. So to increase the stability of the molecule, they can pass that negative charge or that positive charge around the atoms in certain circumstances. It's important to note that molecules that have resonance can have a positive charge or a negative charge, like I was mentioning, or they could even have a neutral charge. Resonance generally occurs when you have a double bond next to an atom in these three different circumstances, and I will be giving examples. So let's start with if we have a double bond next to an atom that's electronegative. All right, so we have this molecule, this amide right here. And my tablet, quit screen sharing again. Is it back now? Okay, I'm sorry about that. Anyhow, we have this very electronegative atom, which is an oxygen. Fluorine is the most electronegative atom on the periodic table, but oxygen isn't too far behind. And we have a double bond here that's connecting the carbon to the oxygen. You'll learn a lot more about this particular type of group, which is called a carbonyl, later on. And we also have this lone pair, which is present on the nitrogen. So in this example, I can draw the lone pair on the nitrogen, depositing its electrons into the single bond between the carbon and the nitrogen. And then the electrons that are in the p orbitals in this double bond, they can be deposited into a lone pair on the oxygen, and we get this resonance structure. So this is our resonance structure. We started with a molecule that it didn't have a formal charge, but it did have an electronegative atom, and it did have another atom with a lone pair and a double bond. So we get this resonance structure if we shift things around. Does anyone feel comfortable explaining either out loud or in the chat why we have the formal charges on either of these two atoms? Well, since I just talked about this, I don't want to dive too far into it, but if we look at this nitrogen again, it has 4 bonds around it. So although it's meeting the octet rule requirements, it's got those 8 total electrons, it does not have 5 electrons around it that it wants to have. So it's going to have that positive charge. But for the oxygen, if we look here, oxygen wants to have 8 total, it wants to have 6 electrons around it, but if we count up, it's got 7. So it's got 1 more that it wants to have. Electrons are negative, it's going to have a negative charge. So that's how we do an electronegative example with a neutral molecule. So you have a couple questions. So Julia is asking, would the first resonance structure's oxygen have 2 lone pairs? Yes. I didn't draw them in, but it does have 2 lone pairs. And then Joyeuse is asking which atom is electronegative. And the answer is that both of these atoms are actually decently electronegative. We've got an oxygen and we have a nitrogen. Which one of these atoms is more electronegative though? We will talk a little bit more about this later on, but oxygen is more electronegative than nitrogen. So if you had to pick an atom to put a positive charge on, we'll talk more about this later as well, nitrogen is going to be like more stable, I believe, with the positive charge than an oxygen. So that's why this resonance structure can occur. All right, let's go ahead and do a negatively charged example. I'm gonna go and draw a carboxylate ion. So we see that there's this negative charge on this oxygen. And I talked about how oxygen is electronegative. So oxygen, it's okay with having a negative charge, but it's still pretty unstable, just like that game of hot potato that I was telling you all about. So I can take the excess electrons from this oxygen and put them into this single bond between the carbon and the oxygen. If I do that, I'm going to have to move the electrons that are in the pi bond in the double bond between the carbon and the oxygen. I'm going to have to move them and localize them as a lone pair on this oxygen up here. So my resonance structure is actually going to look about the exact same. The only difference is I've switched the location of the double bond. So it's gone from right here to right here. And this molecule carboxylate is decently stable because it's able to play that game of hot potato with the negative bond by passing it all around. Well, at least around between the 2 oxygens, if that makes sense. So in a similar note, I'll go ahead and do an example with a positively charged resonance, a positively charged molecule which has resonance. So we have this molecule, and we have a positive charge on our carbon. This is an example. I know Taylor was asking, and some other people were asking a little while ago, why we generally avoid, don't have to calculate formal charge on a carbon if we see it hanging off. Well, here, this carbon doesn't have 3 bonds. This is not CH3, this is CH2. So it doesn't have those, it's not meeting octet requirements, and it doesn't have the amount of electrons that it wants to have around itself. It's got that positive charge. So we can do a resonance structure to reduce the strain on this carbon and pass the positive charge around the molecule. I'm going to go ahead and I'm going to draw the electrons from the carbon-carbon double bond, localize them on this carbon right here for the first resonance structure. So now we have 2 CH2s on the ends, both of which have a positive charge, and we've got 1 negative charge. And if we add up the individual charges on each of these atoms, we will find that the overall charge for our molecule is not changing between the resonance structures. Our last resonance structure is going to show the lone pair, or the extra negative charge on this carbon, being passed to the double bond right here between this carbon and this carbon. And if I do this, I will get rid of not only the positive charge on the end carbon, I'll also get rid of the negative charge on the central carbon. And now we have a molecule like this, where we have essentially passed the positive charge from this end of the molecule to this end of the molecule. And that does promote some stability right there. Now, another way that you might see the resonance for this particular example drawn is like this. You might see, instead of this middle resonance structure being shown, the double bond going directly from this double bond to this single bond. Now, it's okay to draw your resonance structures like this, because technically this is still what's happening, but it's just good to know that you could see either of these forms occurring, like if a TA draws an example, or you might draw them like this. For the resonance problems, we wouldn't take off however you chose to depict them. We have, this structure does occur, but it's definitely, we'll talk about it a little bit later, it's a minor resonance form. So either of these depictions, too long didn't read, is acceptable.
Wait, I don't see a difference between what you draw on the top and what's on the bottom.
Well, if you look here in the bottom resonance structure, we have 3 structures for this pathway. I show this carbanion forming, which is different from here. Here I show the electrons from this double bond jumping over the carbon and landing over here. That's fine. Totally fine to show it like that, but some people do like to show the electrons localized on the carbon. You guys are gonna, I believe, be doing sapling this summer as well as in the fall, and on some of the sapling resonance problems, they like you to show this central resonance structure, so I wanted you to know that it exists, but know that it's also fine to draw positive resonance structure problems out without that middleman, if you will. Does this kind of make sense? I know we're getting a lot of questions. Oh, somebody's asking me where the carbon is. Thank you for pointing that out. Yup, I dropped a carbon there. Does anyone else have any other questions about resonance? Because this is super important. You will be seeing resonance structures in basically every single concept we teach. If there aren't any more questions, I will go ahead and pass the baton to Samantha to do the next part of the lecture.
Thank you. So I'm Sam, if you don't know me. Let me screen share, AirPlay. Can all of you see this? Okay, let me turn it right. Can you see that?
Yep, looks good.
Perfect. Let me get out of this real quick. So I actually can no longer see the chat very well. So if anyone has questions, just feel free to shout it out or something. Or if you want to answer a question that I have, then feel free to shout out. But basically, we are still talking about resonance just because it's such a big topic. And so 2 rules you want to remember for resonance is that 1, you don't want to break single bonds or move single bonds. And so something else I like to think about with this rule is essentially look for double bonds or triple bonds. So we're actually going to be using an example that Sydney just used. Here it is. So sorry about that. So if we just wanted to look at the bonds between carbons here, you'd see that you have this double bond. I highlighted that in blue. And then this single bond, highlight that in red. If we want to take electrons from either the single bond or the double bond, which one would we choose? What do you guys think? I can't hear anyone, but it's going to be the double bond. And the reason why that is if we were to try to take it from the single bond, you just end up breaking that bond, and then you have like two molecules, and that is weird. That is not resonance. And so there was a question someone had earlier about whether or not the charge is going to be the same. And yes, that's going to be correct. So you'll see here, let me find another highlighter. I'll highlight the charges in green. So you see on the molecule on the left, you have positive charge. On the molecule on the right, you have a positive charge. You just moved where the charge was. And so I'm actually going to show you as well. Let me turn off my phone. There we go, we should be good. So I'm going to draw this molecule again up here. Now I'm going to change it though, so that all the bonds are single bonds. It's kind of ugly. Okay. So what would happen if we tried to move that single bond again? Did I draw that right? Yes. So essentially what you would get is this kind of funky looking guy. You'd have like this and then some other random methyl group on the side, and that is not resonance. That is just making two different molecules, and that is bad and illegal, and we don't want that. And so the second rule, sorry, I'm scrolling. The second
quick question, what did you write after the semicolon? I can't read it.
Let's see. Oh, what did I write after the semicolon? It says look for double bonds or triple bonds. Let me go ahead and fix that. Thank you for asking. That make it clear? Sorry if that was confusing. And so the second rule you want to remember, like Sydney said, you don't want to exceed the octet for any of your second rule elements. So some examples are right here. And so I'm just going to draw another structure. And so immediately we're going to see that we have that double bond again. You're going to think, okay, well, that guy has extra electrons. Why don't we just move him over to get rid of that positive charge? And what happens when you do that is the following. Okay. So what you did was get rid of the positive charge on the, oh my gosh, on the nitrogen. But then by doing so, how many bonds does nitrogen have now? It has 1, 2, 3, 4, 5, which is going to be 10 electrons. We don't want that because that breaks the octet rule. So this is not going to be a viable resonance structure. Does that make sense? Let me know if you have any questions. And then something else to note, and Sydney mentioned this earlier, is that there are a couple elements that can break the octet rule. Generally, you're not going to discuss them this much. Sulfur is one example, so just S. If we go back, let's see where it is. My notes are a little bit different. Here, let's erase this. But if you see this sulfur right here in the middle, it's actually going to have 1, 2, 3, 4 bonds, and then those two lone pairs, which is 6 electrons. And so even though he is technically breaking the octet rule, he is okay. He is called hypervalent. But in general, don't be super duper worried about that. Yeah, there's just a few weird exceptions. Does anyone still need this slide? These will also
for this.
So go
for
ahead.
this example, so there is no resonance structure at all.
No, I believe there's not. You could, I think you saw Sydney do her intermediate structures before. You could potentially, let's think, let me draw this out again. I'm going to draw in the corner, sorry. Three and two. So I suppose you could take the electrons from the double bond and put them on one of the carbons. I think you will end up with something that is slightly less than an octet. That technically would be resonance structure, it just wouldn't be a very favorable one. There will be another example of this soon, so if that's confusing, hopefully that should clear it up. And look like this. Yes? Yes. And so now what we're going to do is go through a few structures. So the answer to this question, do the following structures have resonance? All of them, for the most part. 2 of them will have resonance. And so we're going to go through them. First one's benzene. We haven't shown you how to draw organic molecules yet, so I'm going to draw all the carbons. This might take me a minute. Did that just leave? Can you guys see that again? Sorry about that. So I'm going to draw that. Okay, actually, let's do this first. So we're going to see that you have these 3 double bonds, yes? And we're going to move one of them over, but what happens when we only move one? I'll show you. One, two, three, four, five, six. And so the problem with this structure is that now this carbon, I'll draw the rest of the H's in a second. This carbon now has 5 bonds, and that's breaking the resonance structure. That breaks the octet rule, so that is not a resonance structure. What you want to do is actually move all these double bonds around. So it's like a little carousel. Let's see, 1, 2, 3. Make sure none of them are touching. There's also an intermediate structure you could draw if my pen wants to work. There we go. Which would be just putting the electrons on a carbon instead. So let's put them in this guy. And so why did I draw like that? Double bond, double bond. We will show you a better way to draw these out so it won't take you 10 minutes like me. This guy now both has a lone pair and an H. This in general is not going to be a favorable resonance structure. We'll talk about that in a second. But you can see that goes plus. But you can see that that would be the intermediate structure essentially, because you could just take those lone pair electrons and put them back on that single bond, get rid of all the charges. So now if we want to look at the second example, again, we have a double bond. What we want to do is move them up to the oxygen. So that becomes, I'm going to move this down a little bit. That becomes a single bond. The oxygen now has what formal charge? Can anyone tell me? This oxygen up here is going to have -1 formal charge. This carbon will now have a +1. And so if we actually looked at this again, we can see that we can make another resonance structure. So take the lone pairs from the other oxygen, put them back on that carbon, and you'll get something like this. And as you can see, the formal charge, the overall formal charge will always be the same. So for this first guy, overall formal charge is 0. The second guy, also 0 because +1, -1, 0. Same for this guy. Now we want to do the last one. So you're going to see here that this oxygen actually has some lone pairs. And so what happens when we try to put these lone pairs on one of the carbon bonds is the following. We get something like this. And so we want to think, let's see, is this a legitimate resonance structure? And the answer, I'm actually going to draw this out so it's a little bit more obvious. The answer is going to be no, because we've exceeded the octet rule. If you look at this carbon, it's going to have 1, 2, 3, 4, 5 bonds, and that is not good. Exceeds octet. So this guy looks like he's not going to have a good resonance structure. We are running a little bit low on time, so I'll go ahead and go do this slide and then skip the next one. So basically the best resonance structures are ones that have octets on all the atoms, least number of formal charges, which means basically you'd rather have a charge of -1 than -2. Least separation of formal charge, meaning that you'd rather have all your charge on one atom than like several atoms. And if you have a charged molecule, you want the negative charge to be on the most electronegative atom, like Sydney said. So if you had oxygen and carbon, and let's say they're both negatively charged, you'd rather have the oxygen. Same thing for positive charges. You want them on the least electronegative atom, or the most electropositive. Oops. So if you had the oxygen and the carbon again, those are both pluses. Carbon's going to be less electronegative. You want the carbon. And so I'd be less worried about all these rules and just like the fact that in orgo and Gen Chem and everything really, stability is always going to be key. So if all else fails, just think about what's going to be the most stable. So since we're running out of time, I'm not going to identify the major resonance structure. When we post the notes, we will show that to you, so do not worry about that. And so last thing we're going to do real quick is draw organic molecules. So what you want to remember is that for every bond between carbons, you want to show a line or any other bond, and then at each angle is going to be a carbon. You do not draw the H's if they're attached to a carbon. And so that probably sounds confusing, so I'm going to go ahead and do an example or two. So first thing you want to do is count your carbons. So we're going to count these, 1, 2, 3, 4. Let's do that, 1, 2, 3, 4. And so you see that I put these all at an angle. If you circle the angles and count them, it'll be 4, which is the amount of carbons you have. And you might be like, okay, why don't we draw it like this? Like that should be 4 carbons or something. But then like, what's the difference between that and like a line? Like that is not very helpful. We are not going to do that. That's why we do them at angles, and also because of hybridization and resonance structures and whatnot, which will show you the angles between carbons. And so when you have a double or triple bond, you want to do something similar. First, I'm going to count your carbons. It's 4 again. And so 1, let's think. 1, 2, 3, 4. Sorry, that's a little bit ugly. 1, 2, 3, 4. I'll draw these out next to it so they don't look, yeah, same thing. But the reason why we wouldn't do it at an angle like this, for example, is because if you think about a molecule that has a triple bond on one side, a single bond on the other, that's actually going to be linear. It doesn't really work out stereochemically if it is bent. So that is a no. And the last slide is just going to be more structure drawing. Again, since we've run out of time, we'll just post this online. Does anyone have questions?
Does double bonds, you can draw them at an angle, or they're also going to be linear?
Double bonds, it depends. Let me go back to sharing. Let me just think of an example real quick. Let's do an alkene. This slide. So let's say, that's ugly. So let's say we have this. This is what we're going to call an alkene. Don't worry about that name for now. Just means double bond between carbons. So the actual double bond itself, here, let me just draw it. That'll be easier. It's going to look, oh no, never mind. That's a bad example. Well, since we don't show the hydrogens, that alkene would actually look like this guy. And so the double bond is linear in that case. Let me draw another example really quick. I don't want to keep you guys for too long. So now we would draw that out like this. And count the carbons again. You'd find that it's 6. I'm not gonna, I'll just do it 2, 3, 4, 5, 6. And in this case, the double bond, I suppose, appears linear with regard to the entire molecule, but you'll see that the single bonds are actually at like 120-degree angles because that is, I believe, oh my gosh, sp2 hybridized? SP, correct me if I'm wrong. sp2, yeah. And so the pi bonds, you're gonna have pi bonds going up, down, Sydney, the better. But those will keep the carbons linear to each other. Does that answer your question?
Yeah, I was looking at the image in the bottom over here, like with the carbon, the double bond, like.
Oh, the double bond to the this guy?
Yeah.
Yeah, so you want to think about hybridization and what kind of angle is going to be there. So do you know what kind of hybridization this is for this carbon? It's going to be the same as the other, oh my gosh, the other guy, so sp2. That's going to be 120-degree angle. Does that help?
Yeah, it does. Thank you.
Anyone have any other questions? Okay. Sorry we went a little bit over the time, but unless anyone has anything else they'd like to share, that should be about it.
If you have to go, but you have more questions, I believe me, Sam, and Ashley are all offering office hours later today, so you can come through and ask questions if you want. We'll see you guys all at various times on Tuesday for study group tomorrow.